Hello there, Mr. Sutton bringing you this lesson on the mean value theorem. In this one, we're going to identify values that satisfy the mean value theorem, which has everything to do with AROC and IROC. Specifically for applications, we're going to be using the mean value theorem, or MVT, to explain why a trucker should get a speeding ticket. For a warm-up, here's a real-life problem that's getting realer by the minute. A trucker handed in a ticket at a toll booth showing that in 2 hours she had covered 160 miles on a toll road with a speed limit of 65 miles an hour. Now, we don't actually have toll booths in Massachusetts anymore. We have those little camera scanners above the highway that, basically they get your fast pass and they put it in a computer database somewhere. So they could very easily keep track of this if they wanted to now. Now, let's say that this trucker was cited for speeding. Why? How do we know the actual instantaneous speed was ever actually a number over 65? So pause the video and give this a thought. So here's one way you could approach this. If you're going 160 miles in 2 hours, your average rate of speed is going to be 80 miles per hour. So the average speed you'd have to maintain to go that far was 80, but that's the average speed. That doesn't tell us anything about your instantaneous speed at any given time in those 2 hours. So can we use this conclusion about the average rate of change to make any conclusions about the instantaneous rate of change? If we're talking about the relationship between the average and the instantaneous rate of change, like on that speed limit problem, we're talking about something called the mean value theorem, or the MVT for short. So this theorem has a few conditions and it has one conclusion. Let's talk about the conditions first. In order for this theorem to work, we need a function f that is continuous on some closed interval, a to b. This function also needs to be differentiable on the open interval from a to b. So the standards are relaxed a little bit on this one. It's an open versus a closed interval. Now, if we have these two conditions, continuity and differentiability, then there is some c value, which is an x value, on the interval from a to b, such that, and here's the conclusion of the mean value theorem, f of b minus f of a over b minus a equals f prime of c. So what are we saying here? We're saying if we have a continuous differentiable function on an interval, then there's some x value on that interval that the instantaneous rate of change at that x value equals the average rate of change over the whole interval. There is some c value where the IROC equals the AROC for the whole interval. Now that we've stated what the MVT actually says, let's go into the intuition of why it works. For this, I'll go to a picture here. So here's a function that's continuous and differentiable. There's no corners, cusps, discontinuities, or vertical tangents on this. And we've got 2 points on here, a and b. We've also drawn a secant line from a to b that gives us that average rate of change over that interval. Now we're claiming that since this is continuous and differentiable, there is some x value in between a and b where I can draw a tangent line whose slope matches this secant line, where the IROC equals the AROC for the whole interval. We see that this has to be the case for the following reason. At a, we have some instantaneous rate of change. At b, we have some other instantaneous rate of change. The average rate of change has to be somewhere in between those two instantaneous rates of change. In order to get from a to b on this continuous differentiable interval, we have to go through all the slopes from the slope at a to the slope at b, including this in-between average rate of change. So we're guaranteed, and you can see this visually, there is somewhere we can draw a tangent line that matches this average rate of change. So that's the intuition behind it. Now there is one little tricky thing with the MVT, and it has to do with this closed versus open interval. Although you have to be continuous on the closed interval from a to b for the MVT to work, your c value, your x value, has to come between the endpoints. If you want to satisfy the MVT by finding some x value that makes this true, you can't use the endpoints because the theorem itself uses the open interval from a to b. So the endpoints don't count when you're trying to find an x value where the IROC equals the AROC. For our first real example here, we're going to go ahead and use the mean value theorem. So for this multiple choice question, c is the number that satisfies the conclusion of the MVT for x cubed minus 2x squared on the interval 0 to 2. It's a closed interval note. So we basically want to find out what is the c value that makes the mean value theorem happy for this function and this interval. First thing we need to do is we need to establish we can actually use the mean value theorem. We have to establish the conditions are met. which means we have to verify that our function is differentiable on the interval. Now, we also have to verify that it's continuous, but if it's differentiable, it's already continuous. So if you go for differentiability, you really get 2 of those for the price of 1. So how do we know that this function is differentiable on the interval from 0 to 2? And it's got to be the open interval, because that's what the mean value theorem says. It has to be continuous on the closed interval, but differentiable on the open interval. Well, this is a polynomial. Polynomials we know are continuous everywhere, including the interval from 0 to 2, open or closed. So we're good on satisfying the conditions of the mean value theorem. Now we go for the conclusion. The conclusion says that at some c value, IROC equals the AROC for the function on the whole interval. So we need to calculate 2 things, AROC and IROC. Next thing we'll do is we'll find the average rate of change on the interval. So pause the video and take a minute to do that. All right, to find AROC, we need to do f of 2 minus f of 0 over 2 minus 0. So in this case, f of 2, that's going to be, let's see, 8 minus 8, so 0. F of 2 is 0. And then f of 0 is also going to be 0. If we've got 0 over 2, that is also 0. So this is going to come out to 0 for the average rate of change, which is a nice number to have for an AROC. It doesn't always come out to 0, but it works out that way this time around. Next, we need to find the derivative of the function, the IROC. And this IROC is going to have an x still staying around in it because that's the x we're going to need to solve for down the road. So find the IROC here. All right, so f prime comes out to 3x squared minus 4x, just using our power rule on this. At this point, we are now going to set the average rate of change and the instantaneous rate of change equal to each other and solve. And when I do this, I'm plugging this c value in to my instantaneous rate of change here. So I am going to write 3c squared minus 4c equals 0, because ultimately I'm solving for c, and c is an x value. So pause the video and solve this. All right, so on this one we can factor out a c value, and that leaves us with 3c minus 4 inside. So just using our zero product property, we have c equaling 0 and 4 over 3. Looking at our answer choices, we have a 0, but alas, we also have a 4 over 3. And you got to pick one, so which one should we pick? So here's where you have to remember that your magic c value has to come on the open interval from 0 to 2. The MVT says there's a c between 0 and 2, not including 0 and 2. So because 0 is an endpoint, we can't include it. We're just going to take 4/3, which is the only one we got that wasn't an endpoint. So that's going to be choice D on this one. For this next example, we've got another multiple choice question. Pause the video, read this over, and give it a shot. All right, so we have some function f that is continuous and differentiable on a closed interval from 0 to 4, and they've been nice and given us a table with some values of f across this interval. We want to know which statement is true, which has to be true. So this is one of those process of elimination kind of questions. Let's go through these and see which ones we can knock off. So part A, or answer choice A, minimum value of f is going to be 2. If we look at our table, 2 is the smallest y value that they're giving us. However, we are not guaranteed that that's the smallest y value for the whole function. We don't know what's happening, for example, between the x values 0 and 1. Maybe this function is dropping below 2 and then coming back up to 3. So since we could drop below 2 between the values they gave us, we can't guarantee a minimum value of 2. By the same token, we can't guarantee a maximum value of 4. Sure, that's the biggest y value they give us here, but maybe between the x values 2 and 3, our y value goes above 4 and then comes back down to 3. Now this next one is saying that our function is positive, greater than 0, between 0 and 4. They only give us positive values, but if we're allowed to drop below 2, somewhere in between the table values, we could certainly drop down to 0 in between those table entries. So by this token, we can't guarantee positivity here either. Now part D, or choice D, they're saying that f prime is less than 0, negative between 2 and 4, basically saying that between the x values 2 and 4, we are always, always, always decreasing. Well, we had to decrease at some point to get from the y value 4 down to the y value 2. So the average rate of change is certainly negative. However, the instantaneous rate of change could be doing a whole bunch of different things in between there. We just don't have enough information to conclude that we're always decreasing. So although AROC is less than 0, not necessarily all of the x values are decreasing derivatives. That leaves us by elimination with choice E. So this is a yes, because nothing else works. But why does choice E work? So here they're saying we have a C value between 0 and 4, where the IROC is 0 at that C value. If we're talking about guaranteeing the slope being a specific number, this is a really good candidate for the mean value theorem. So let's check out the average rate of change and see if we have an average rate of change of 0. Because if we do, we can make this conclusion. Looking at our table here, the average rate of change from 0 to 4 is going to be 2 minus 2 over 4 minus 0, which is essentially 0 over 4, which is essentially 0. So we do have an AROC of 0. And they also told us our function was continuous and differentiable on the interval 0 to 4, the closed interval. So we're covered on continuity and differentiability there. So that means the MVT says that this AROC has to match the IROC for some x value in between 0 and 4. So choice E is true by the MVT then, and we're going to pick that one. For this last example, given a table of function values for a continuous and differentiable function, approximate the rate at which the function's changing at x equals 5. Pause the video and brainstorm how you might do that. All right, let's see if we got the same idea. So if you only have a table to work with, you can approximate the slope at an x value by finding the average rate of change of an interval that the x value is on. Now, one reason we can do this is because, well, there's really no other options. They didn't give us any other information. But for another thing, since this is a continuous and differentiable function, we know that the average rate of change of an interval that the x value 5 is on is going to equal the instantaneous rate of change somewhere on that interval. It might actually be the rate of change at 5. It might not, but it's really all we got. Now, for best possible results here, and to make yourself feel better about doing it this way, use the smallest possible interval. So the interval we're going to use then, 4 to 6, right? Because 5 is right between those. So let's do f of 6 minus f of 4 all over 6 minus 4. Now, they told us f of 6 and f of 4 in the table. That's 180 minus 16 all over 2. So that's 164 over 2, which comes out to 82. And that's the best approximation we're going to get on this. So, not trying to be mean, but this lesson's over. Till next time, Mr. Sutton signing off.